Hello class, this is CSE 4410, Section 2, and possibly Section 1, Spring 2024, Week 3, Game Programming. Now, this is going to be a video format of the lecture slides for Chapter 2 as it pertains to the book here. This is going to be a recap of all the material we've covered in Chapter 2 so far, plus other content that we may not have gotten to yet, or content that we haven't gotten to yet as of the time of recording. I'm recording this, as of now, I'm recording this because of a storm warning, and we have to switch over to an online mode of teaching. So in lieu of having any in-person meetings, I am recording this video specifically as filler for the storm warning looming over our heads right now. Anyway, so I have created a whole new project through Unity Hub. What I did was click New Project, and then I just typed in a project name, select 3D because it's going to be a 3D game. I then clicked Create Update. I already have the project open right now. Here we are. Now, so this is going to be, some of this is going to be review from the slides. So, when we have a new project in Unity, we have a sample scene with a main camera and a directional light. No game objects yet. That's gonna be a bit for later. So, let's start building out the entire scene. Let's begin with a cube. So, if I go to game object here, I have 3D object down here, and I can choose from all sorts of different shapes. I'm gonna go with a cube, so I'm gonna now have a cube in the scene. If we look in the hierarchy, we can see the listings of every game object in the scene right now. And this here is called the scene. If I adjust my camera, we can see a few elements on the scene view more clearly. We have this thing here that displays where our X, Y, and Z axes are going and how they're oriented in 3D space. Also, we can switch from an isometric view and perspective view. What I want to do now is move this cube to the origin, so we have a center. For which we can start our. I just want everything to start from the center. If you look at Unity tutorials online, it may advise you to keep game objects within the first 10,000 units of the origin. Anything further than that may start to suffer from floating point precision errors. In Unity, the units as shown in the inspector on the right-hand side of the interface, it gives us a position that is in. It never says what kind of units they are, but in practice, they are thought to be meters, which is often the case with all sorts of 3D modeling software. You can think of these as any abstract unit you want, but the common convention is meters. So, with that in mind, the cube is currently at -5 on the x-axis, negative 5.1 on the x-axis, -1.3 on the y-axis, and -2.4 on the z-axis. If I want to have that be at the center, all I gotta do is replace those three values with 0. So, one other thing about Unity, as I've talked about already, is the x coordinate, the x and y axes, the x, y, and z axes. So what do they mean? Well, in a Unity project like this, the x-axis, the y-axis, the y-axis denotes height. And the x-axis and z-axis, those denote coordinates on the floor If you think of the XZ plane as the floor, then Y is the height. This might feel a little bit backwards depending on what kind of 3D modeling software you use. Blender, for example, if I can open this up right now. If I start up Blender, for example, and look at the interface for that, you'll note that the X and Y axes form the floor, and the Z axis denotes height. You see, Unity uses something called left-handed coordinates, where if you were to take your left hand, point your finger up, thumb out perpendicular to your pointer finger, and then middle finger pointing towards you. If the thumb denotes the x-axis, and the y-axis is your pointer finger, and the z-axis is your middle finger, this is how Unity denotes its coordinates. It uses left-hand coordinates because to make this gesture requires your left hand. Blender is a little bit different. It orients all of its axes a little bit differently, and Z is the height. Y is it in Unity Y is the height? My best guess as to why that is when you have stuff on the screen, you have XY coordinates already. So you already have width and height being used, so Z must mean the extra dimension, which in this case means depth. In mathematical contexts, you have an XY plane already, where oftentimes it's X is the input, Y is the output. But if you want to go to 3D, you have to add a third axis to that, and that usually means that X and Y are inputs and Z is the output. And typically Z usually means height. So, this distinction is important if you're ever going to be working with Blender and Unity at the same time, because the coordinates are going to be different. The axes are going to be different, I should say. But it doesn't really matter, because if you are to make a 3D model in Blender and then import that into Unity, Unity will have no problem converting from one coordinate system to the other. Basically, it'll just rotate the whole model, because under this coordinate system, it's basically a 90-degree rotation about one of the axes. So that's one thing about Unity that might differ from certain 3D modeling programs. It's how they use X, Y, and Z, which is height, which axis is height, basically. So now we have our cube. I want to make this cube pretty big. So, in the two classes that I'm going over this content with, what I did was I scaled it up so that the cube is 20 units long. That means I'm going to scale up its x. So that means I'm going to scale it up on the x-axis by 20 units and 20 units along the y-axis, right? Well, if we did that, remember, the y is height. So it means I just made it taller. We don't want that. So I'm going to reset this back to 1, and it's the z-axis that I have to scale things along. So I'm going to type in 20 for the z scale, and because this is going to be the floor, I want to squish this cube even further. So I'm going to type in 0.1. So now I have this floor. Let's call it a floor. I'm going to go here, rename this. I can also rename it through the inspector here, so I can just, instead of having the word cube, I would have the word floor. There we go. Okay, now I have a floor. I want also a couple of walls. So I'm going to go to Game Object, select Cube. Now I have another cube. I want that at the origin. I am going to then I'm going to have to turn this from a cube into a shape that can be suitably used as a wall. So for that, I'm going to stretch it along one axis, maybe stretch it like 3 units up and down. So now we have a wall, and now I want to squish it along one axis. So let's just squish it along the z-axis, so 0.1. And then I'm going to stretch it along the x-axis so it becomes one wall that goes on this edge here. So I'm going to change that to 20. And now I can move this cube into place. You see these 5 tools here? Well, this is really 6, but anyway. These 6 tools are bound to the Q, W, E, R, T, and Y keys on your keyboard. I don't have a QWERTY keyboard, so it doesn't really help for me. But if I press W, it will change to the Move tool. If I select the cube, I can drag. I can move the cube along any one of its 3 axes or any one of the 3 planes. I'm just going to move it along one of the axes because that's where we want it to move. It's a little bit hard to see, but there are 3 planes. You can move it across 3 different orthogonal planes. But really, I just want to move this cube to position 0010. Alright, so now we have a wall. If I press Ctrl D, I duplicate the wall. Now I can just move it along the y-axis to 0, 0, -10. Or I can just punch in 0, 0, -10 into that cube's position. Oh yeah, how am I changing my view in the viewport? Well, scroll wheel zooms in and out. Holding down and right click rotates your view. Holding down right mouse button lets me pan around the view. Holding down middle mouse button lets me pan across the view. So now, I have 2 cubes, left and right. But now I need 2 more cubes, front and back. Now I could just make another cube by going here, selecting game object, or I can just duplicate an existing cube, rotate about the y-axis 90 degrees. Well, it doesn't matter which way direct you rotate it, it's gonna be the same for our purposes. So you can either type in -90 or +90. So I'll just do -90, enter that, and instead of instead of position 0, 0, -10, I want position 0, no, not 0. I want position 10, 0, 0. Because if you look here at this icon here, the x-axis is actually pointing towards the camera. Well, not really the camera, it's pointing towards you. So it means if I am to change the x position by moving it along the x-axis, if I change the position to here by changing the value like this, it's going to move towards the camera. Or either it's going to move towards it's going to move towards you, if that makes sense. Because we have a camera here, but it's not the same as this camera, if you can call it that, in the scene view here. I guess the more proper term is to call it a viewport. But anyway, that's not quite the right position, so I want 10, 0, 0. So now we have another wall towards the front. If I duplicate this once more, Ctrl D, and move it along the x-axis here, I can push it back, and now we have another wall. So now we have all 4 walls. They're all called cube, cubed, cube, cube, which is not great, but not terrible. What I want to do next is, enforce some organization to this. So I'm going to create an empty game object. So under game object, create empty, and it's going to be at some coordinates in the game world. So I'm going to name this game object walls, and its position is something something something. I want it to be at 0, 0, 0. And now with this walls empty object at the center, I can control click each of these 4 walls in the hierarchy, and then I can drag and drop all 4 walls onto this walls game object. There we go. So what this does is it makes it so that, well, they're not all the same object in that their meshes are combined, but rather they're the same object in that they are connected to each other in a way. So wherever I move this parent object that I have called walls, all the other game objects attached to it as children also move. Wherever it goes, they go. And I can move it up and down, or I can scale it as much as I want. Let's put it back. So this is also why I want it to be in the center. So that way they won't be... It's a little bit hard to describe, so I'm just going to have to demo it to you. To take out these game objects from being children of another object, you need to select them and drag them outside of the game object that they're attached to as a parent. So what happens if I had the walls at some random coordinates like this? This is why I want it to be centered, because if they're not, this is why I wanted the walls game object to be in the center. Because if they're not, and I made the cubes children, well, their coordinates are going to be the same coordinates as the walls game object, but with their signs flipped. That's because the walls object has its own local origin, and by moving all of these walls onto the walls game object, by moving these 4 cubes to be parent objects of the walls empty game object, they are going to basically change their position values so that they are not under the global grid, they are now under the local grid of the walls game object. Which means if I try to center this now, it's going to be offset. So, as I said, I don't want that to happen. So instead, I'm going to undo that change where I made the cubes child objects of the walls object. Press undo, press undo, and press undo. And now instead, I want to make sure this is in the origin, and then move all of these objects back to the walls object. So now I can now treat them as though they are one object. So now we have our outer walls. Let's make another copy of this wall. Take it out of the walls game object. So now, if I can rotate the camera so I'm looking from a top-down view, I can now slide this wall, click on this scale tool here, and now the now the tool looks a little bit different. Instead of arrowheads, I have these little knobs that I can pull and push to change the scale of the wall along any one of its 3 axes. So now I can do that, change the size of a wall, and then change it back to the move tool, and then duplicate, and then move, no, save, duplicate, and then move another copy of the same wall, into a different position. Let's scale this one a little bit more. Let's say like that. What we need to do now is partition this space into a series of rooms where we have basically we are to partition this into a room where we have the player just exploring around and hopefully beat up some enemies. So this is going to require duplicating the wall several times and then rotating them into position and scaling them accordingly. We just want to have a couple of walls. Basically, we want this space inside to be partitioned into a series of small rooms. Let's continue with that right now. So I'm going to change to the rotate tool. You see how we have these now red, green, and blue arcs? I can now rotate about these arcs, or I can hold down Shift and increment by, what is that? What is that increment? Anyway, it's going to rotate about, okay. Yeah, those are 15-degree increments. Anyway, I can rotate about 15-degree increments like this and ensure that it's going to be rotated 90 degrees. Because if you saw that, I incremented by 6 tick marks, and then each tick mark is 15 degrees. 6 times 15 is 90, or I can just punch in 90 into the inspector. Anyway, I want to keep on scaling these around, so I have to squish that down, squish that cat, duplicate this one, slide this back here, and then move this one here, and then here, and then for fun I can rotate one of the walls a really weird angle, like this. Or I can try to have one wall butt up against another wall, so it looks like they're part of an even larger wall. Move around like that, and so I can get a good top-down view of what get a good view of what the walls look like from above. Change the scaling of different cubes accordingly, possibly move some walls out of the way, duplicate, basically building up a space for our player to explore around. Let me move this back. Alright. Duplicate. It's Control D. Then I can move this into position and then possibly scale it a little bit wider, like that. Right, so let's go with this space. Now, what the book advises that we do is place a few extra lights around the scene. Let's do that real quick. So, lights come in different types, and one of them is the directional light, which is what the scene came with. This basically mimics the sun, in which we have parallel light rays coming in from every direction. They're all parallel light rays come in from everywhere, and they're all going in the same direction. This mimics sunlight. There are other types of lights that I think is best demonstrated if I turn off the sun. Delete that. Where did the sun go? Well, why does it still look like... Why does it still look like it's lighted outside? That's because we have a skybox. We'll probably work with that in a little bit. But I want to turn the sun off so I can demonstrate a couple of lights. So if I go to Game Object, Point Light, hard to see because it's way below the rooms, so I'm going to change its origin to be 0, 0, 0, and now look at that. We have a light. Let there be light. You know, let me move these walls. Let me move these 3 walls a little bit. So now, alright. So now we have a light, and it is emitting light in all directions from a single source, a single point. Much like a light bulb. If you don't count the base that it screws into, the socket it screws into. So let's move this light a little bit closer to the wall. Push it in like this. Lift up a little bit high. You notice how the light is casting light. You know how it's casting light into the next room even though it shouldn't? That's because it's not obeying physics properly. For that, I think I need to switch to mixed. No, not that. No shadows. Let's pick out hard shadows. And now it's gonna cast proper shadows. Getting a second. Anyway, have this light just casting light within the one room here. I set the hard shadows. Real-time indirect band shadowing is only supported for directional lights. So maybe it has to be soft shadows. Well, that doesn't really change anything. Okay, so there we go. In case you're getting errors, I have it set to mixed and soft shadows, but hard shadows seems to also work. The reason why we have these lights is to light up the rooms a little bit. So I'm gonna take this and, much as before, duplicate it a few times, place a few lights at specific locations on each wall, so it looks like each room is being illuminated. One thing we can also do is change the intensity of each light, or we can make it a different color. So if we want a more if you want a light that's closer to, say, candlelight, you would want a light that's a little bit towards the yellow side, like this. Maybe towards the orange side, like that. So there we go. A little bit of an orange light. We call that a cool light. No. That's a warm light. My mistake. Warm lights are more yellowish, orangish. Cooler lights are more closer to daylight and maybe towards the blue end of the spectrum. So a cool light would be pure white and possibly a little bit towards the blue end, like this. But if we want a warm light, then we want something that's a little bit more towards the yellow-orange area on the color wheel. There we go. I can also select all these lights, and through the inspector, I can assign them all the same color, like so. There we go. Duplicate. Copy paste some lights here, 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 here. The textbook advises don't go overboard with the lights because it may result in performance issues. But maybe this is enough lighting. Let's put back the sun by creating a new light. Create game object light. Directional light. Let there be directional light. So now it's going to shine light from every direction, and again, all the light rays are parallel. It doesn't matter where in the game world the directional light is, but because all the lights are coming in from somewhere and they're all going parallel. So it doesn't matter where we put it as long as it's there. So now we have this room. And one thing we can do about the directional light is we can adjust its rotation. So we can change the rotation to our liking so we can have light going in a specific way. The shadow type on this one is also set to no shadows. Let's change that to soft shadows or hard shadows. And then change it so it looks more like we are See, if I have it pointing up, then it's nighttime. But if I have it pointing down, then it's much closer to daytime. But if I have it something like as though it's right on the horizon, then we don't really have much light into the room, but we can still see the shadows that are being casted by the walls, like that. And now it's nighttime by rotating it way up high, and now it's more like a daytime if I have it pointing much lower. I want it at a good angle like this so it looks like it's casting shadows into the room. That looks good, right? So now we have a whole room. And that's going to be our entire level. One other thing we can do is to organize this whole scene. In the hierarchy, I have cube, and point light, point light, point light, point light, point light, point light. Let's organize that. So, I'm going to call this one, I'm going to call the first game object inner walls, change its position back to 0, 0, 0, have that be at the origin, and then I'm going to select all the cubes that are already I'm going to select all the cubes that aren't forming the outer walls, and then I'm going to drag and drop them onto the inner walls game object, and then I can close that. I am also going to create another empty game object, call that lights, and then I'm going to select all the point lights that I have in the scene, drag and drop that onto the lights game object, and close that. I can have the directional light outside because it's its own thing, or I can just have it be part of the lights object. Doesn't really matter. It's this way I just want some semblance of organization. I just want this whole scene to be organized. So now, hopefully our scene is organized, we can move on to having the player. So in game object, I am going to go to 3D object and create a capsule. But now he's like way below the ground, so I have to change the position to be 0, 0, 0, and our player is currently stuck in the floor, but that's not a problem. I can just raise him up, and boom. Now he's on the floor. But now we have a little bit of a slight issue here, and that is the walls might not be tall enough. Well, if you look at the bottom, the walls are actually extending below the floor, so really there are one of two solutions here. We can either make the walls taller, or we can raise the walls higher up, or we can just move the floor lower. So the floor, we can just lower that, and not too much, or else we'll start to peek into the void, just enough that we can have the player comfortably walk around the rooms with no problem, without getting stuck onto anything. In fact, this might be a bit of an issue, so I am just going to scale this one down. In class, you may have seen me scale down the player itself, and we could do that. Maybe a scale of like 0.8. No, that's a rotation, not that. 0. So maybe something like 0.7, 0.7, 0.7 is a good scale. So just small enough for the player to again just walk around each room without any issue here. So move the player here and look at this corridor. That's not tight, is it? If the player can pass through that no problem, then it should be okay. So now we have our player, and the next step is to attach the main camera onto the player, so that way we are mimicking a first-person view. So this capsule is, well, just a capsule. It's a primitive object. It doesn't have anything special about it. It's just a giant pill. So it's not a fully rigged 3D model of any sort of character. Rather, it's a stand-in for a character. in professional game development, you might not necessarily be working with finished assets from the get-go. Rather, you may be working with primitives that you'll be swapping out for complete game objects later on. Or, you might have to throw the whole thing away, start from scratch. And that's okay, because that's not unheard of when it comes to prototyping. And especially if you are starting at the prototype phase. You might have a game that's all primitives, and that's okay. What's more important for our case here is to get a game that works, not a game that works and looks good. So it's okay that our player is a capsule. In fact, let's call him not capsule, player. There we go. Now, I want to move the player back at the origin so I can properly attach the camera onto the player. So right now the camera is viewing this wall head on. I want to move the camera so that it is at the origin. And then if we take a close look at these two objects here, the camera is just a little bit above the player. If I move the camera a little bit down so it looks like it's inside of the player's head, and I'm using that term loosely, then we can call that a good position. And now we can move the main camera to be a child object of the player. And now we're done, right? Not quite. We need to write scripts now. So now we have the scene, but nothing can do anything because there are no scripts that let us do anything. I can click play and nothing happens. So, I'm going to pause the recording so I can pull out the slides that have all the code so I can reference that while I program away at writing all the scripts. So, one thing that the book describes is how to write a script and understand how it works. So this first script is actually going to be attached to a test object. So I am going to right click in this empty space here in the project view, go to create and click on C# script. I am going to name this script spin, and if I double click it, in my case, in my setup, it's going to open up Visual Studio. You can go to edit. You can go to, come on now. You can go to edit, preferences, and under external tools, you can actually change the code editor to be whatever code editor you personally use. I personally use Visual Studio, simply because that's what I'm used to. So anyway, double click that spin script, and when we do that, it's going to open up like this. See all this code over there? See all this code up here? I didn't write that. Unity did. So that's the one thing about Unity. It lowers the barrier to entry for creating a game to the point that all you really gotta do is throw in some assets, move them around to your liking, and then write some code that tells each game object what it should do. This character is firing bullets at another character. This character is an NPC, and when clicked on, he's going to have a dialogue option and a shop interface. Click on this object, it's got an Easter egg, and you have and then it also gives you 10 coins. So, all this code is pre-written by Unity itself when I had created the spin script. So I want to demonstrate how rotations work in Unity. So what I'm going to do is I'm going to type in a, let me zoom in. One thing I can do with the Visual Studio is zoom in on the text. So hopefully this is plenty readable for you. It's a bit on the large side, so maybe that's okay. So 177% zoom. Not that kind of zoom, but anyway. I'm gonna type in a variable here, and I'm gonna do it like this. Public float spin, and I'm gonna give it a value. Let's go with 3.0 f. So now I have this public variable here. It's a floating point value. It's a floating point value because it's got a decimal point. But more specifically, it's a floating point value. It's a 32-bit floating point value. If you did not have the f there, it's going to be interpreted as a 64-bit floating point variable. Unity only works with floats and ints, so those are 32 bits of information. Anyway, in the update method, and in C#, functions, they're not called functions, they're called methods. That's just one thing about programming languages in general. You may learn these things under certain names as it pertains to a specific language. They might be called different things in other languages. So, as an example, in C#, there is a data structure called a dictionary. If you've ever worked with Python, you might remember that as an associative array. If you remember your data structures from, say, C++, that is called a map. So, same kind of data structure, but different names for things, basically. That's just something also to keep in mind if you're going to be working with different kinds of programming languages. So anyway, I want to type in some code. So that is transform.R rotate, and then it's going to take in 3 values. That's going to be 0. This actually be speed. My bad. Let's leave it at lowercase s spin. One thing about variable names, you do not want to have them in conflict with class names. So this is capital S spin, this is lowercase s spin. So I'm just gonna copy that, paste that into here, and then 0. So what this does is it's going to rotate a game object about its 3 axes, x, y, and z. It's going to not do anything about the x-axis because that's a 0-degree rotation. It's going to rotate about the y-axis by 3 degrees. And then it's going to rotate by 0 degrees about the z-axis. Okay, that's all well and good. So what is this update method? It is a method that this method is going to be called once every frame. So every frame, transform.rotate is called, and it's going to spin. It's going to rotate. This spin script is going to be attached to a game object. And that's because it inherits from a class called monoBehavior. Nearly every script that you'll ever write will inherit from monoBehavior. Sometimes you might have scripts that don't inherit from monoBehavior, but for this first part of the course, all scripts you'll write, they'll inherit from monoBehavior. So this, among other things, allows you to attach this script onto a game object, and once it's attached, every time a frame is rendered, update will be called, and it's going to call this method here, where it's going to apply a 3-degree rotation on the object that it's attached to every frame. If I close that interface, let me stop playing that, and now we need something to attach this script onto, and I'm just going to create a random test cube. So I got a game object, 3D object, cube, and it's nowhere in sight. That's because it's under the floor again, so I have to move it back to the origin. Maybe I want to have it a little bit further away from the player. Save that, and to drag and drop a script, to attach a script onto a game object, you can just go into the assets panel that has all your scripts here, drag and drop onto the cube. So now, if I hit play, the cube is spinning. Now, this cube is spinning 3 degrees every frame. Now, I have a pretty powerful computer, or at least I hope I do, still, because it's got a Ryzen 7 1700 CPU and a GTX 1070 graphics card. So if I go under details, performance, you can see my computer's specs. That's a lot of memory. But then again, maybe that's not enough anymore. Graphics card is at a toasty 75 degrees Celsius. CPU usage, like that. Well, I don't know if you saw that, but I accidentally shook the window too hard, and under Windows, that gesture means minimize all other windows. So let me just unminimize everything and get the screen recording software back open. What had happened was, and maybe you saw it yourself as well, this cube is spinning at a rate that is dependent on how fast your computer can render each frame. That's not good, because if this is a competitive game, you are basically accidentally creating a pay-to-win game. And whoever wins is whoever can afford the most powerful computer. Or, there's a more devious way about that, whoever can lag out everyone else. So, this cube is spinning at a rate that is dependent on the frame rate. We don't want that. To fix that, I am going to go back to Visual Studio, and this spin value here, I am going to multiply that by something called time.delta time. It's going to multiply the spin rate by however much time it took to render the frame. So it's going to rotate 3 degrees every second. It's just that a frame is typically rendered in a fraction of a second. So it's basically 3 degrees per second, but over a time span that is a fraction of a second. Say 1/30th of a second, or maybe 1/60th, if you like your games at a smooth and buttery 60 FPS. Anyway, it's going to then rotate at a fraction of that 3 degrees. But by multiplying by time.delta time, we are effectively making the rotation rate of our cube independent of the frame rate. It's called frame rate independent. So if I run this script now, if I run the game now it rotates at 3 degrees a second, which is all fine and dandy, but maybe you want the cube to move faster. When we made that spin variable, what we did is make it available to edit in the inspector. So what I can just do is type in, I can just type in whatever angle I want, press enter, and now it's going to spin at however much I want. Or I can make it negative. And have it spin the other way. Now it's spinning a few times a second. That's pretty fast. The thing about the inspector is you cannot edit values while the game is running because it won't save. If we want to change the value, we need to do it while the game is not running in the Unity editor. So if I want to change this 3 degrees to something else, say pi degrees times 100, because apparently I can do that in the Unity editor. I can type in something times something else. It'll do the math. And now I am spinning at pi 100 degrees, if that makes sense. There we go. Now the cube is spinning at pi 100 degrees. And if I stop the game from playing, it's going to stay at that 314.159 degrees. Okay. So now we have a cube that's spinning. We're not really going to use that for the player, but we can, some of the base code we can use. So I'm just going to shove that right out of the way. What I'm going to do now is start writing a different script. This script is called mouse look, and if I press, no, if I hold on, and then double click on that script, it's going to create a new script with all this boilerplate code already written for me. The first thing I'm going to write is something called an enum, which is where you associate numeric values with special names. So let me just demo one for you. So public enum day of week equals, is Sunday the first day of the week or is it Monday? Oh, let's say that for the sake of example, Sunday is the first day of the week. So Sunday equals 0, and then Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and then I close all of that and wonder why it's not working. Oh, it's because of that extra equal sign. There we go. So I have created an enum, and each of these keywords, each of these words I have defined, they have a value associated with them. So Sunday is assigned to 0, Saturday is assigned to 6. If I then write something like public day of week day, and then close that, if I go to the inspector, I'm not gonna see the script itself because it's not attached to anything. As I said, this mouse look script is going to be attached to the player. So let's do that now. Now if I click on the player object, I now have a mouse, I can now see the mouse look script that's attached to it. So here's the one neat thing about an enum. When you edit it when you edit values of that enum type, it's a drop-down menu. How neat is that? Well, we're not going to be working with days of the week, but if you're going to be working with a time-based system, you might need days of the week, or maybe you need months or seasons or whatever, or what have you, or a day-night, or a day versus night system. What we want for our mouse look script is 3 modes of movement, and those modes are going to be rotation, it's going to be X movement only, Y movement only, or both. So I'm going to go back to the mouse look script, delete all of this, and start typing away at public enum rotation axes, and then in curly brackets I'm gonna start a new line. Mouse X and Y equals 0. Mouse X equals 1. Mouse Y equals 2. And then under that, I'm going to declare a variable of type rotation axis enum. So public rotation axis equals. No, I forgot the variable name. So I have the data type, I need the variable name. Axes equals, and I'm going to assign it one of these values. And for that, I'm going to have to type in rotation axes dot. Let's pick one of these. So the code that I have on screen, and this is the same code in your PowerPoint slides. Mouse X and Y. Save. That's part 1. Part 2 is going to be writing code in the update function here. So we have 3 modes of movement. We need to write code that does the following. If it's in one mode, do this movement. And if it's in another mode, do this movement. If it's in another mode, do this movement. So I'm not going to write all the code yet. That's going to be the next step. What I'm going to do is write the if and else if statements for that code. So if, I'm going to also move this curly bracket to there. That's just how I write whatever code standards that, if you have whatever coding style you write, whatever code style that you have, be consistent with it. For me, that's going to be placing the curly brackets like this. You might be doing something else. Just be consistent with how you style your code. Read a style guide. Follow it religiously. So, for now, I'm just going to write in if axes double equals, not triple equals, double equals rotation axes dot mouse X, then do some code here. Else, if axes double equals rotation axes dot mouse Y, do something else. Else, do something else. So, I'm just gonna throw in some comments. Horizontal and vertical movement. Vertical movement only. Okay, so this is going to be where we write our code later. So what is this script going to do? Well, it's going to move the camera according to which way we move the mouse. There's 3 different modes to that because we have to move along the mouse's x-axis, also along the mouse's y-axis, or possibly both axes at the same time. So we're doing each one separately so we can understand how each mode works. The first mode is actually going to be the simplest mode of all. I'm going to write in a public variable here, public float sensitivity horizontal, spelled H-O-R, and then I'm gonna assign that a value of 9.0f. So, I'm going to say transform that rotate, and then for the three Euler angles, because the rotate method accepts, the rotate method takes in three values, and those three values are Euler angles. Those are rotations about the x, y, and z axis. And because I have IntelliSense working on my installation of Visual Studio, it actually says what those rotations are. It applies a rotation of Euler angles.z around the z-axis, Euler angles.x around the x-axis, and Euler angles.y around the y-axis in that order. So, well, basically it's going to do the z rotation, then x, then y. Now, one thing that this thing can do is it can accept something called a vector tree. It's basically a data container that can hold three values. And those three values are called x, y, and z. Or we can just write in three values individually, which is what we're going to do here. So we're not going to rotate about the x-axis, but we are going to rotate about the y-axis. So I'm going to say input.getAxis, and then in parentheses, I'm going to write in quotation marks, mouse space x. M in mouse is capitalized, x is also capitalized. Times our horizontal sensitivity up here, and then 0. So now, this script is going to have us rotate. It's going to rotate the camera about the y-axis whenever we move the mouse side to side. The mouse has its own x and y movements. So side to side movement is the x-axis. For us to rotate side to side, requires us to rotate about the y-axis if you think about it. So if it feels like it's kind of backwards, well, hopefully I'm doing a good job at trying to explain it. So if you have this little figure right here, if we move side to side, and if we recall that the y-axis is going up, you can see why this is supposed to be rotations about the y-axis. So that is our first mode of movement, and if we try the code right now, so this player object is going to have the mouse-look script attached to it. Before we continue, we need to replace this capsule collider. We're going to replace this capsule collider with a different kind of thing. So I want you to remove this and then click Add Component and type in Character Controller. I already had this typed out, so that's why it's already saying, hey, do you want a character controller or a character joint? I want character controller, because we're going to be using that later. You'll see. If I press play now, and I look side to side, nothing happens. If I look at the player in the hierarchy and then look into the inspector, that's because it's set to the wrong mode. I want the mouse X mode, and now I can go around and around and around, look around as much as I want. But I can't move up and down yet. We're gonna write that next. So go back into your code editor. We're going to fill out this block of code next. So first thing we need to do is add in another sensitivity. So this is called public float sensitivity vert. This is going to be also equal to 9.0 f. Here's the thing about vertical movement. I'm going to say right now, this is going to rotate about the x-axis. And if you recall, let me just say that, I remember I said that the y-axis is going up and down, and if you move your head side to side, that is a rotation about the y-axis. A rotation about the x-axis is actually, if you can imagine I screwed my head and I rotate it like this, that is a rotation about the x-axis. If I move the mouse up and down, and I still have that skewered to my head, and if I'm to move the mouse with my head skewered like this, and that skewer rotates my head every time I move the mouse up and down, that is a rotation about the not the y-axis, the x-axis. So, I'm going to, if you think about it, if we have this up and down movement, there are physical limits. Think about that for a second, but let's just say it would not be comfortable at all. I have this little thing here. Like, if we could just freely rotate about, sorry, let me just get this view really big for a second. If we could freely rotate about, if we had a character like this and we wanted to if we wanted to rotate side to side, that'd be very simple. But remember that the head is has a camera attached to it. So if you wanted to do an X rotation freely, it's gonna hurt. So yeah, we want to impose limits on how far we can rotate about the x-axis. So, shrink my camera down, and let's start adding in those limits. Public float minimum vert equals negative 45f. Public, not public float maximum vert equals 45f. So now we have limits to how much we can rotate up and down. I'm also going to create a private variable. Private float vertical rotation equals 0. This is going to be a variable that stores our current rotation. And for our purposes, we don't want that to be modified by anything else. It must be handled only by the script. So we can't even edit this in the inspector. Nor should we even do so. So that's why it's a private variable, not a public variable. So we have those variables written down. If I go into this block here, I can now type in the following code. Vertical rotation minus equals, so it's going to decrement some amount. So it's going to decrement our rotation by some amount. And that amount is, I'm just going to copy paste this, but swap out some variables. So it's going to get, what this getAxis method does, it's listening for input from the mouse, because it says mouse X. It's going to be either X-axis movement from the mouse, or in this case, we want Y-axis movement from the mouse. So it's going to be input.getAxis mouse Y times our vertical sensitivity in that line. Then we want to make sure that this rotation does not exceed the minimum or maximum allowed vertical rotation values. So I am going to say vertical rotation equals mathf.clamp, and then I'm going to copy paste vertical rotation, and then copy paste minimum vert, and then copy paste maximum vert. So this clamp function is from Unity's math library called mathf. It's a collection of common math functions, and one of them is called clamp. So it's going to restrict a value to be within a specific range. So if we somehow have a rotation that goes to 50 degrees, it's gonna say, no, go back to 45 degrees. Okay, so now we have a vertical rotation. What are we doing? Well, here we are saying rotate by such and such degrees. We can't really do that here because we want to enforce that rotation is within a specific range. So we are not saying rotate from your starting position to some new position. We are saying set your position. It's the difference between saying go up the street 3 miles north and go to this exact location. So, for this to work, I need to also get the current horizontal rotation. So, flow, horizontal rotation equals transform dot local Euler angles dot y. I need to save that so I can then do this. Transform. What we have previously done is use the rotate method to rotate something that was already rotated. What we're doing is assigning that rotation directly ourselves, so we can't use the rotate method anymore. We need to say transform dot local Euler angles equals. We're going to assign it a value, and that value is going to be in the form of a vector tree. Remember that a vector tree is just a data container that has three values called x, y, and z. So on the right hand side of the equal sign, we just say new vector tree, and then this creates a new vector tree data structure. And inside, it's actually not a data structure, but it's a class. Don't worry about that. It's going to be within the constructor that we have our three values. So that's going to be vertical rotation, horizontal rotation, and 0, because we don't have any z-axis rotation. So remember when I pretended I had my head skewered and I was rotating my head up and down? And then if I just rotated my head side to side, those were already x and y rotations. Those were already x and y axis rotations. Where's the z-axis in all of this? Well, imagine I skewered myself through the nose and I tried to rotate my head like this. That's a z-axis rotation, but we don't have that on the mouse because a mouse can only do 2 dimensions of movement. If you wanted rotation like that, we need a separate input device for that. We don't really do that with first-person shooters unless your character just ragdolls on the side and he's dead. Maybe it'd be more applicable to say a spaceship or an aircraft. For now, we don't have any z-axis rotations. So this is the final code. I'm going to save all of that and then I'm going to play the project again. If I try to move the mouse, nothing happens because it's not set to the right mode of movement. We had mouse X already working previously, so if I change that to mouse Y, and I look up and down, we can now look up and down. So now, if we want to move side to side, all we gotta do is have a way to change the mode on the fly, so now we can move about the X and, oops! Now it's broken. So now is the time where we need to write the X and Y movement. What I'm going to say right now is that it's going to be copy-paste. So we need to program this mode of rotation, X and Y, both of them together. So what we're going to do is copy-paste all this code. Well, no, this code. I don't want to copy the comments as well. So I'm going to paste that here. So now we are doing vertical rotation about the y-axis, but we also need to do horizontal rotation about the... Okay, let me back up. When we move the mouse side to side, that's going to be an x-axis. No, it's a little bit confusing, as I said. Move the mouse along the x-axis, translates the movement, rotation about the y-axis. Move the mouse along the y-axis translates to rotations about the x-axis. I'm talking about the mouse having its own set of axes and the corresponding player having its own rotations about its axes. Okay, so that code starts off with all of this code. What we need to do next is change the rotation about the y-axis, not just leave it unchanged. So we have one other addition to make to this code. We have already we've copied it from here and pasted it into here. So what I need to do next is say float delta, and a delta is a small change in something. That something could be anything: small change in time, small change in pressure, small change in money, small change in anything, small change. Float delta equals, and I'm going to assign the value of input dot get axis, and I'm going to say mouse x, and then times our horizontal sensitivity. Oh, not there, here. So now I have a delta, and now I need to add that delta to our horizontal rotation. And that's it. So now if I play the scene now, in the inspector, it's already set to mouse X and Y movement. And look at that. We can now move the camera however we want. Yay. Okay, so now we have camera movement. Our next step is actually player movement. So I'm going to get set up with that code, and I'll meet you in a bit. Alright, so the next step, we need to write a new script. Create C# script, and I'm going to call it FPS input. Press enter, and if I reload script assemblies, give it a bit, hold on, double click, and it's going to open up in Visual Studio some more boilerplate code that Unity already provides for us. So what we could do is go back to the spin script and copy this, paste it here, though it's probably not going to be a spin anymore, it's going to be more like a speed. And then I'm going to go copy this from the update method and paste it into this update method. And since I changed it from spin to speed, I may as well change that. Let's just get this code nice and organized. There we go. So now we have this code here. So if I save this code, this is FPS input. I'm going to then wait and then attach this script to the player. So now if I click on the player, now we have a mouse look script and an FPS input script. If I press play, well, nothing's really happening. If anything, the camera's moving. But that's because, well, I left it at transform.rotate. I want transform.translate. So let's try it again. Reload. So if we let this play out, well, here's the thing. That is a translation about the y-axis, which means we're now ascending up and up and up. If you look into the inspector over here, it's climbing up steadily. So, given several hours, we're going to end up into outer space, where outer space is defined as 100 kilometers off the ground. So, that's not what we want. We don't want the player to just go up into the stratosphere. No, we don't do that. We want the player to move based on key presses that we make on the keyboard. But this is a good starting place, actually, because then we can just modify that code a little bit more so we have movement according to whatever buttons the player presses. By default, in Unity, it's the W, A, S, and D keys that are used as a stand-in for the arrow keys, but this will also work with the arrow keys. So let's go back to our code and change this translate function to something else. So we have our speed variable. I'm going to write this in. Float delta x equals input.get axis and then horizontal times speed, and then float delta y equals input.get axis vertical and then times speed. And since I don't want to move along the y-axis, I am now going to write it like this. So transform.translate, the first value is delta x. So this is movement about the x-axis. There is no delta y. We don't want to translate about the y-axis, so 0. And then delta z. Okay, I actually mislabeled the variable. So this should be not delta y, delta z. So there we go. So now we have the player. So now we have player movement down, right? Let's test it out and see if our input system works. So, as before, we can move the mouse about and we can look around. If I press the arrow keys, I am going way too fast. He's hacking! No man, I'm in creative mode. Anyway, we are just gone. So, we now have the same problem as before, where previously when we had that spinning cube, it would spin at a rate that was dependent on the frame rate. We have the same problem here. So, it's not just input.getAxis times speed. It has to be that times time.delta time. So, this way we have the rate of movement. The speed of the player should not be dependent on how fast your computer can render frames. So, if it were, then whoever has the fastest computer wins. Or, as I said, a more devious way to win is to lag everyone else out. So, to keep our operations frame independent, we need to multiply by time.delta time. So now, we fixed the speed issue. Let's try it again. And if I press the forward arrow key, and I try to hit a wall, I find that I don't collide with the walls, rather I phase through them. Also, wherever I look is the direction I go. So, by just looking up and going forward, I can fly. So now we have two more problems to fix. We can't have the player go through walls, and we can't have the player fly around. So, this is how we fix it. Remember how I said, take out the capsule collider and put a character controller instead? Well, here's why. We're actually going to move the character using the character controller instead. So here's how we do that. Well, we have a character controller already attached to the player. what we do next is this. We go back to our code editor, and I'm going to create a private variable that looks like this. Private character controller, and I'm going to call it character controller. So now I have this private variable. It's going to contain a reference to the character controller component that is attached to our game object. How do we get that reference? By calling a special method called getComponent. Here's how that works. I'm going to copy paste this because this is going to have a null value until we write in the start function the getComponent method. So here's how it works. I paste character controller equals get component, and then in angle brackets I'm gonna type in, or I'm gonna copy paste in, character controller, and then left parenthesis, right parenthesis. So now we have a reference to our character controller. But it says in down sense is saying this private member can be removed because we assigned the value but we are never reading it. So Visual Studio is smart in recognizing what variables you're not using, but the thing is, we actually need to use it. Here's how. So, remember when we multiplied by time.delta time? Undo that change. So now we have delta x equals input.getAxis horizontal times speed, and then delta z equals input.getAxis vertical times speed. Won't that make us fly around at super duper fast speeds again? Won't that make us go at ludicrous speeds again? Well, yes, but we're actually going to be multiplying by time.delta time in a different location. You'll see. What we are going to do is this. We're going to create our own vector tree. Let's call it like this. Vector tree movement equals new vector tree, and then I'm going to pass it in delta x 0 delta z. Remember that we have movement about the x, y, and z axes, but the y axis is for height that goes up and down, vertical movement. We do not want the player to fly. We don't want the player to fly. So there is no delta y here, it's going to be 0. That y value in the vector that we made is going to be 0. What we're going to do next is we're going to take movement and then say times equals time.delta time. So what this does, it's going to multiply our movement vector by time.delta time. It sounds a little weird, but it's basically scalar vector multiplication, if you recall what that is from linear algebra. So vector tree is, well, if you remember linear algebra, it is a group of numbers. If we have a vector multiplied by a scalar, that means multiply every entry in that vector by that same value. So it's basically multiplying. It's the same thing as we had before, where we multiplied delta x and delta z by time.delta time individually. It's just that this is a little bit faster because we're kind of saying that, but in one line. So we're not multiplying these values individually, we're multiplying the whole thing as though it were one unit, which I guess it kind of is. There's one extra step. It's a little bit hard to grasp, but basically our movement is about the character's local axis, and we want to translate that into global. We have to translate that movement about the local axis into movement about the global coordinate system. So I'm going to say movement equals transform direction, and then parentheses, movement. And then finally, I am going to get the character controller here. I'm going to say character controller dot move. And then I'm going to pass in the movement vector. So if you remember, say, physics, a vector, in this case, it basically describes which way are you going in three-dimensional space. The length of that vector says, how fast are you going? Right, actually, the length of that vector says, how much are you going to move from one frame to another? And that vector says, I'm going to move from this location, from where I am now. I'm going to add the x, y, and z values of that vector to my current location so that in the next frame, I'll be at this new location. So now we have the update function updated so that now, instead of using transform.position to change our... We're not using transform.translate to change our position anymore. Rather, we are doing that using the character controller now. So now if I press play, and if I try to move with the arrow keys now, well, I still have the problem of I'm going up and down. But if I try to collide with the walls, because this character controller, you can collide with walls with it. So I'm hitting the walls, I'm hitting the walls. Hit the wall, hit the wall, hit the wall. I can't phase through the floor, but I can still fly out of the level. So that's one more fix we need to do. We need to keep the player from flying away. Well, here's the easiest way to do that. I'm going to go back into the code in our first-person shooter. We are going to write in another public variable. So public float gravity equals 9.8. Actually, negative 9.8. And then append that with an F. So, that kind of sounds familiar, doesn't it? That's gravitational acceleration on Earth. So that is 9.8 meters per second. Or about 32 feet per second. It is 32, right? 9, 8, 27. Yeah, that's about right. Okay, so now we have to make a few more changes to the update method, and here's what they look like. We're going to use that gravity, and basically we're going to have the player susceptible to gravity. The easiest way is to just say public float gravity, and then we just have the player. If the player were to ever fly up somehow, the player's just going to fall back down. It's basically that. But then gravity is an acceleration, don't worry about it. So, in our code here, right before our movement times equals time dot delta time line, there was actually one more thing we have to add. And it's to make sure that the player does not move too fast. Here's what we're going to do first. Movement equals vector3 dot clamp magnitude. And then we're going to pass in as a first argument movement and the second argument speed. So if you think about vectors as being little lines, I should say little arrows in 3D space, the length of the arrow it's called its magnitude. You can change the length of the arrow, but it'll still point in the same direction. The thing about velocity is that it is a speed with a direction. So this movement is basically how much are we going to move in one frame. But we want to clamp that movement so we don't move too fast. So this clamp makes sure that that length of that vector is never too big. Because if it's any bigger, that's cheating. Okay, so now we have that. We're going to also say movement dot y equals gravity. So this way, if our player were to ever somehow fly, the player's going to fall back down to the ground. So I'm going to save all that. I'm going to click play again. If I move using the arrow keys, I can move around, move around, move around. And no matter what I do, I cannot fly off the ground. So we fixed the flying around issue. You might notice a slight issue, and this is going to be actually one of the last things to fix. Because it turns out there was a fourth issue. Hey, here's one of the little lights in the corner. Anyway, if I stop moving, my hands are off the keyboard, but it just moved. What's up with that? My hands are not on the keyboard, and I just moved. So what's going on? Well, here's what's going on. That gravity vector is pointing downwards, but depending on how our player is rotated, that down isn't always pointing down. So even if it's at some slight angle, you're gonna slide. We're applying downwards movement, but that downwards movement isn't always going to be downwards. So that's one more thing we need to fix, actually. So it depends on which way the camera... It all depends on which way we are looking at. So here's how we fix that. So it's a little bit tricky, but follow my lead. If we click on the player, and we go back to the mouse look script, set that mode, the mouse X. What we need to do next, remember the mouse look script we wrote? We need another one, but it's attached to the main camera. So now the main camera has its own mouse look script. Change that one to mouse Y. So now if we play this, we can move around. So what we did is separate the two modes of movement into two. I guess you can imagine it as one game object is going to be the player looking around left and right. That's going to be rotation about the y-axis. The camera has to move up and down independently of the player, and that's going to be x-axis movement, where the player moves their head up and down. Is this making sense? So, if I have this little guy here, I'm going to detach his head for demonstration purposes. So, really, what we have here is the player is going to move side by side, and that's going to be accomplished by rotating the player object itself. If we imagine this player's head as being the camera, it has to move independently of... It's got to be able to move independently of the player while still being attached to the player itself. Does this make sense? Anyway, so that's the one fix that you have to do. And now, it means our first-person shooter now works. Camera movement works. Player movement works. Everything is working. We can't fly through walls, we cannot cheat. At least I hope not. We can maybe just a little bit clip into the wall, but really, our game is now fully functional. It doesn't look good, but it works. The point of this first chapter is to make a game that works. Not necessarily look pretty, but we will be getting into that a little bit. So, this is going to conclude the entirety of chapter 2. For section 2, I want you to view this video in its entirety, which is almost 2 hours long. It's basically a recap of everything we did. It's a recap of everything we did, plus all the content that we can't really get into because of the storms living up our heads at the time of recording. The next time we meet section 2, we're going to do a question and answer session on basically debugging. And hopefully after that we can start with chapter 3, which is where things get interesting, because we're gonna start having the player guns blazing, basically. So, follow this video, follow the slides. When we meet again, we're gonna have a question and answer session, a debugging session on what needs to be fixed. What did you have something break, and if so, did it break in a weird way, and how do you fix some weird issues? So, see how far you can get, and then we'll meet back. Hopefully, when the storms have cleared up, we'll meet back together and talk about our project then. For section 1, by the time you see this, hopefully you will be further along with the project, but you can still use this video as a good reference of how to get the level up and running. So we have walls, we have corridors we can walk down, we have little lights that we can use as guidance, or just illumination. We have little corridors we can walk around, and we could have, well, later on, we will have enemies to attack. So that's gonna be until chapter 3. So, section 2, follow as far as you can. We can't really meet on Monday as of time of recording, but hopefully by then the storms will cleared by Wednesday, so we can have a question and answer on any sort of questions or debugging issues that we may have. And hopefully by then we can start looking at chapter 3, because as I said, that's where we go in guns blazing, literally. Alright, that's gonna be it from me. Stay safe. Section 2. Section 1. Stay safe also, because even if the storms have ended, the roads might still be white even by Tuesday. So stay safe, everyone. Stay warm, stay dry. View these videos, and we'll continue on our normal schedule without any sort of interruption, such as the campus is closed because of storms. Alright, thank you, class, and have a good day.